Hello everyone. In the last chapter we talk about motions, how to describe motions, how things moves, and it's characterized by speed and velocities and also accelerations. Okay, to summarize, speed is how fast things move, and it's in units of how many meters in 1 second, or how many miles in an hour, or how many feet in a minute. And so it's distance versus time. And velocity is also related to speed. It's a word about the speed and direction. So speed and velocities are closely related but slightly different. Velocity has more information about, if you say where this car is going, you must say, well, it is going, what is this velocity? And the velocity is like 65 miles away to the northeast or northwest and so on. But if you say how fast the car is running, you only have to say its speed. Say 50 meters per second or 50 miles per hour, and etc. And then if you want to, so how fast speed is changing, that is the concept we talk about, the acceleration. Acceleration is the change in velocities or change in speed. Or in physics, we actually call it acceleration and deceleration. Or simply, if you have a coordinate system, if you have positive acceleration and negative acceleration. In fact, the acceleration is the change in velocity, and is in directions. Now, when we come to this chapter, it is about how do you cause acceleration? How do you make motion? How do velocity changes? How do you get things to move in a simple case? That is, the simple answer is, remember the force. So I write over here, what is force? In other words, that's our daily experience tells us if you apply force and the things will move, okay? And when things move, you block it and also apply a force in the opposite direction, it will stop. So force is that make the things move, okay? And so then force and object, how they interact, that is governed by the laws of motion. And this is attributed to a great physicist of all time, arguably, and it's Newton. Okay, now the topic of this chapter is Newton's law of motion, related to how things move, how force and object and mass and acceleration are related. Okay, so Newton actually has 3 laws of motion. Okay, so now we are talking about the first law of motion. So here is how it is stated. Okay, Newton's first law says every object remains at rest or in a uniform straight line motion unless being acted upon by an unbalanced force. Alright, here's a video, you can look at it. But now, what does that mean? So every object remains at rest, alright, okay, or in straight line motion if there's no force. And put in a simple words, I will ask you in a simple words, what's in your word? What is Newton's first law of motion? Put in your own words. Okay, copying down this doesn't make it count. Okay, so don't copy down this, but this will help. That's why you go to school for, to able to read the formal scientific text, but then understand it and be able to explain it to whoever don't know yet. Alright, so now first law says everything remain at rest and or in uniform straight line direction motion unless being acted upon by an external force. So what does that mean? First, okay, I bring in here, imagine we're in an outer space. Here's the object. Newton says if the object is at rest, okay, if there's no force, it will stay at rest. See, it stayed at rest. But unfortunately, there is a force. Okay, so actually the Earth also attracted, of course there's a force. But it was very, very far away over here. I pretend there is no force. The first law says when it is already in go straight line, it will continue go that way forever. See, it's going continuously going that way forever. So in other words, if the object, say a pencil or a vase on the table, okay, at rest, if you don't bother it, will not move. So that's Newton's first law. And also Newton's first law has a second clause saying if it is already moving in a straight line, but usually that part is a little bit puzzling, or you may be object to that, it will continue to move forever. Okay, but that is only happening in the outer space, because if you have something moving in outer space, okay, there's nothing bothers it, it will really travel forever. So let me just show this again. Alright, this again simulated outer space, and we demonstrate Newton's first law approximately. If there's no force, look at the green ball I grabbed. Very far, assuming there's no force, if you don't bother it, it will just stay there. Okay, but of course there's a force. And of course, if Newton's law says if it's going in a straight line, it will continue going that way. Because on the Earth, you don't see this very often. You say, wow, Newton says things will keep going forever if you know no force. Well, you kick a soccer ball, it will stop. Well, the soccer ball will continue move forever if there is no air resistance, or if the gravity not bring it down to the Earth. But then the second part of Newton's first law is a little bit hard to demonstrate on the Earth, because there's always something stop it. But in outer space, his first law, look at my green ball. Okay, so it goes straight line if nobody bothers it. Okay, so if nobody, nothing. So see that one? Go. If there's no force, you keep going in a straight line forever. So that's what Newton's first law would say. So now, then here is actually a question, and in your own words, what is Newton's first law? Yeah, and it says, well, since at rest or going in a straight line, you keep that way, which means if there's no force acting upon it. Alright, so you will come up with your own version of a statement of Newton's first law, or you can make the shorter sentence the better. Okay, if you leave things alone, it will stay the way it is. So that's very simple. Again, over here, illustrate if the object, no outside force, if it's already at rest, it will stay there forever. If there's no outside force, if the object is already moving with velocity, it will move, it will never stop, of course. And then that's Newton. How? But what if there is a force acting upon it? What is force then? It's an interaction between object. So the force you can feel, and I punch the door, or somebody pushes you, and that's force, and you can push something. So if when you have a force, then you will change the velocity, you will change the status of the object, or it will. At rest, if you push, it will move. If it's already moving, if you stop it, a force in the opposite direction, it will stop. So then, how force causes acceleration? And here comes Newton's second law. So, Newton's second law of motion is related to the acceleration. So, the first law says, well, if you leave it alone, it will not move. Okay, it will keep going. But the second law says, well, if there is a force, and then the status of the object will change. Okay, or it will cause acceleration. Force will cause acceleration. So, formally in our textbook, they will say Newton's second law says the acceleration of object is directly proportional to the net force acting upon it, and it is inversely proportional to the mass of the object. Here we get some videos, and I probably don't want to show it here, but then you can watch when you get these notes. So, what does that mean? So, Newton's second law says, and of course here I use my simulation again. Now let's demonstrate Newton's second law. So I grab it with my hands, okay, my cursor. You can play this, I will let you to play with this. And then my hands will apply a force on the object. If there's no force, it will stay there. Like look at the yellow ones. And if you apply a force, small force, it will accelerate, which means, see, it's accelerating. Okay, and so it means that if you have bigger force, it will accelerate more. Small force, it will accelerate a little bit. With no force, it will stay. So, see, small force and small accelerating. Okay, and big force and big accelerating. So then, and that's very straightforward. And then you will say, well, here is a question. Okay, you understand that statement in your own words. That's the question. Okay, what is Newton's second law? Well, the acceleration, we will say force cause acceleration. You know, force, when you apply a force, it will move. And that relate to your experience. Like, you know, you punch a volleyball, it will accelerate. You punch harder, it will accelerate more, and so on. So that's the second law. It's very straightforward. But Newton make it formal. So the acceleration is proportional to the force, which means the more force you apply, the stronger the acceleration. But acceleration is always in the direction of force. Alright, so then use your own words. Well, and then you just have to translate this statement to your own words. The acceleration of an object is directly proportional. The word directly proportional means the net force acting upon it. And also, but there is another part of the Newton's second law. And it says is inversely proportional to the mass of the object. So what that means, which means inversely proportional to means the more mass, well, it's harder to accelerate. So that also fit our experience or our intuition to things. Saying if you have a big chunk of snowball, if you kick, it will move, but slowly. Okay, and if you have a smaller soccer ball, you kick with the same force, it will go like crazy. But if you have small, tiny tennis, you kick with the balls, and it will go very fast. Of course, the bigger and the harder to accelerate. That's what this inversely proportional to the mass means. Okay, the acceleration is inversely proportional to mass and is directly proportional to the force. So, now, go back here. If you want to understand Newton's first law, second law, alright, okay, smaller force, smaller acceleration. Okay, so if the Earth actually attracting this everything with some force, the closer it is stronger. The farther away the Earth's attracting force is weaker. You see this green ball I'm in my hand? If I let go, there's a small force. It's accelerating slowly. Okay, but if you have it here, so you see when it's getting closer, the Earth the attraction force is stronger. See, for the yellow one is accelerating faster. But then if you go further away, the smaller force and accelerating slow. So the mass, but if you have the same mass on the Earth, well, it's the bigger mass will accelerating slowly. See, it will accelerating very slow. Okay, so that's the idea. So then, if you have a question, I will ask you, what's Newton's second law then? In your own words, you will say, what? The harder you push, the stronger you push, the faster the object will accelerate. Or in your own words, the more force, the more acceleration. Or the more mass with the same force, well, the less acceleration. Or that's what inversely proportional means. Well, mathematically, it is represented by this formula. Okay, much easier. So look at here. Mass, the acceleration, is directly proportional to the force. So it's a formula to force on the top. which means the bigger force, the bigger acceleration. And is inversely proportional to mass, then you have a mass on the bottom, dividing by the mass. So the bigger the mass, so no, from mathematics, you know that the bigger number, when you divide, it will get less. So that's the formula. So now here's the example, all right? What is the acceleration of a 1 kilogram car if the force is 5,000 newtons? The force is in the units of newtons. So, which means this much force is applied on this car, which has this mass. What is acceleration? Well, put in the formula. And so force 5,000. Okay, this should be newtons. That's a type, oh, even though it's correct, 5,000 newtons. Okay, the more you have more acceleration, then you have this, 5 meters per second squared. That's straightforward. Alright, force units are in units of newtons. And also this form can be sometimes, so there you see there are three quantities in this formula. Acceleration equal to mass divided by the force. But if you know mass and you know force, and you use force, you use mass to divide into the force, then you get an acceleration. Okay, and then of course, there's the three quantity. If mathematically, if you know two of them, you can calculate the other one. So, and very often people write like this. So you multiply the force mass to the other side, so it's where force actually equal to mass times acceleration. So if you know the mass, if you know the acceleration, you know, okay, the mass, 5 kilograms object is accelerating like a rocket, and there must be a force. So what is the force? You simply multiply mass and acceleration together, you get the force. And in fact, mathematically, this formula and this formula are the same, equivalent. Again, mass is, yeah, from chemically you will say, well, mass is how much material is there, how much the amount of substance are in there. Or in physics, mass is resist change, okay, or mass equal more inertia, which means resist change. How it works, mass times acceleration equals the force. That's Newton's second law. And also, then, of course, force. And then there are four fundamental forces: electric forces, gravitational forces. The gravitational force is one of the fundamental forces, okay, which means everything on Earth will experience a force attracting between the two objects. So the force is depends on the mass of this object. On different planets, the gravity attraction is different. But so here are the gravity on different planets. So, and basically depend on how big the planet is. So just look at the gravity and attraction, and then you will know basically the mass, the proportion, relative proportion of the mass of different objects. See, the Earth is blue, is this much, 1.0, which means we have a 9.8 meter acceleration due to the attraction. But on a Mars, and it has smaller gravity. So then if same thing, compare with the same mass. But if I ask you, which one has more mass from this, Mars or the Earth? Well, obviously the Mars, because it says, well, less gravity and proportional to it. And Jupiter and Earth, which one has more mass? Jupiter then. So if, in fact, the gravity is really proportional to the mass. Okay, and what is the attraction of the moon? Well, it's very small. It's not shown here. So we talk about the force cause acceleration. There are fundamental forces. Of course, our hands can push something. That force later you will know is actually normal force, and it's electrical in nature. But then it's not a fundamental force. It's because of those forces, and things push each other. But there is a fundamental, gravity is one of the fundamental forces, and it's called the universal law of gravity. So that you need to remember. So it's on our textbook. I sort of highlight here. Okay, what this law says is like there is an attractive force on any two objects. That's a big statement. So Newton made that big statement. when he made some of this statement, people said, wow, are you really sure about that? I would imagine, because there's why I don't see a table attract a chair, okay? And why they don't pull into each other, or why one person don't attract to other thing, is this really true? But Newton says, well, it's true, not only true, and I have a formula for it. And here is the formula over here, okay? And he has this formula over here. And this formula says the force between two objects depend on the product of the mass, right? Depend on the product of the mass, and also depend on the distance between them, okay? The more mass of the two, you multiply together, the more mass, the more force, okay? So you multiply them. And of course, the farther away and the less, okay, the weaker. The force become weaker when the objects are far away. So then some people in there, okay, give me the formula. I start calculating this, calculating the force between them. So when you calculate the force, you find out that, well, and then Newton said, well, the formula also have a gravitational constant g here. So he gave this number. But then it turns out that his magic is that this number is very small. In fact, of course, this number may not be accurate. Don't quote it. Actually, 10 to the 11, negative 11 or negative 12. I don't remember exactly, but that's on every textbook. Okay, so, but the fact I want you to remember is that this number, constant g in front of it, is extremely small. It's 10 to the negative 11 or negative 12 or something like that. Okay, I'm not forcing you to remember, but you might remember that constant is very small constant. And so constant that if you put the normal object like a table, mass of the table, mass of the chair, and distance, 5 meters, 10 feet, and put them to do a calculation, well, you get some reasonable number between these three, right? But we multiply with this constant in front and become negligible. Okay, you don't notice it. Okay, right? Then you say, well, Newton played the trick. He said there's a force attracting everything to object, but if you do calculating, that's so small that you don't notice it. But he said force exists. Well, how can I check such a small thing? Well, he said, well, the formula is still correct, not if the one of the object is huge. So if you have a small number here, and one of these number is huge, okay, a huge number, like if you put in the Earth, the mass of the Earth. So mass of the Earth is this, 9.9, 10 to the 31st kilograms. That's a huge number. So a very small number multiply with a huge number, and then of course this one is sort of a normal number, and then like eraser or stapler or computer or something like 5 kilograms. But this one is a matter of Earth. So between the Earth and the other normal object and the distance between them is the radius of the Earth, and then this come, significant numbers. So I will ask you this question. Okay, Newton says there's an attractive force between any two objects. They're pulling each other, but why don't you see it between table and chair on the Earth's surface? But you will say, well, it is very small. Okay, the force is very small, unless one of the things is very big. Okay, and see, this is me. Okay, 60 kilograms. But this is the Earth, but that's huge. And then the distance, and you put in all the numbers, and it becomes a reasonable number. So that's the universal law of the gravity. So, and the attractive force definitely between the lines of these two. So the attractive, so A attract B and B will also attract A. So the two objects will attract. That's the universal law of gravity. If you want to use state to say what is the universal law of gravity, you will say, well, there is an attractive force between any two objects, and its strength is given by this formula. and in which this number is very small. And unless one of the mass is huge, you will not get anything that significant can be observed. Unless you have Earth or Sun and Earth, Moon and Sun and so on, then they will have significant force. Alright, so remember, I will ask you the question, what is the universal law of gravity? And here is the answer. Well, once again I use this game to demo universal law of gravity. So this is an attractive force between any two objects. So this is the green ball. I grab it in my hand between these two, and the mass of the Earth is huge, but the mass of the object, like say a tennis ball, is weak. But if you use that formula, there's a force. If you let go, then since there's a force, Newton's second law tells us if there's a force, it will be accelerating. See, the green ball, let go, it will go accelerating. Of course, it bounces back. So anything that bounces between the Earth and something is because of the gravity. The two things just attract each other, right? So it's when it's very far, the acceleration is weaker. If you had a bigger ball, and you will see that it has bigger, will harder to accelerate, but the force is stronger. So you see, go, accelerating. So then it's always attracting to along this line. So if you put the green ball over here, where it goes, let it go, it will go towards the center. That's demonstrates the gravity. So it's an attractive force between any two objects. So they will go this way, or far away, and it will be weaker. So you see, if you go very far, the white ball over there, the attractive force will be inversely proportional to the distance squared. That's far away. You let go, the white one, look at the white one, it's accelerating, but it's still there. So, in fact, and if you go very far and very fast, you can escape Earth's attraction and go away. So you basically accelerate. Then of course, now you see what I'm after. So if you put this, the gravity will always pull in the back. But Newton's first law says always tend to go straight line. So the gravity will yank it back. So this game is interesting. If you go very slow, the Newton's law, first law says I won't go straight line. But there is a force, therefore I will accelerate towards the force. So if you go very slow, then it will crash into the Earth. Okay, and crash into the Earth, right? You go very slow. There are three situations. You go very slow, it crash into the Earth. Very slow and crash into the Earth. Very close, you kind of like your basketball or ping pong ball and bouncing on the Earth. Okay, and but if you go very fast, okay, it will. The Earth is still attracting it, but it will not deaccelerate enough, but then you get farther and farther away, and the Earth gets becoming weaker and weaker, so it's escape. So there are three situations. One is very slow, it will crash into it, and very fast, it will go away, run away, escape. Okay, and then there is a sweet spot, and so that you have the right speed and right direction. So then Earth attracting it, but it's not totally falling into, and that's why it settles into an orbit, or is circling. See that one, the green one? It's going away, but then it slows down, now it's pulling it back. So it is circling. So this game is trying to make it, see that one is going that way, and you can think about it, it's always falling, but nowhere to land. See that way? So then the goal of this game is to make all three circle the Earth. See, all three circling the Earth, right? See this? All right, so that's the one of the assignment later on. Again, the Earth attract any object on Earth is called a universal law of gravity. So it's closer, a stronger force. Newton's second law says, well, strong acceleration. Okay, and far away, weaker acceleration. You see, and even far away, even far away and very small acceleration, okay, and very far with less acceleration. So then people were interested in what is really the acceleration at a different place because of different force and of course different acceleration based on the formula we have. Okay, A equal F divided by mass. So when it's far away, when the F is small, the acceleration is weaker. When it's closer, acceleration will be bigger. So what is actually the acceleration over here and near the Earth's surface? So that's what we care, because that has something to do what we live every day. What is the acceleration over here? Okay, when it's close to the Earth, looks like green, the ball, that has the acceleration. Whether it goes outward and inward, its acceleration is the same. So that acceleration is 9.8 per meter squared. So that acceleration, if you think this question, okay, and that acceleration is 9.8 meter per second squared. So you say after being released, a ball thrown straight upward from the bridge will have an acceleration of this. In the air, it has acceleration, which means its velocity is constantly changing. So which one? The answer is this. So that what actually means that wherever it is over here, you either toast upwards or downward, and near, so look at the yellow one. Its acceleration is this much. Towards the Earth is 9.8 meters squares. So if you're going up, it has that acceleration. You're going down, it also have that same acceleration, because acceleration is proportional to the force, because the force is towards the Earth. Again, therefore, it's downward direction. Then it is downward direction. So that acceleration around the near surface is 9.8 meter per second squared. Now let's solve a problem of our exercise and Newton's second law of motion. So if the 10 Newton strength force applied to an object of 3 kilograms, what will be the opposite acceleration? Okay, and this is directly application of Newton's second law, and we just use the formula. Okay, and we worked out this in class. For those of you who are online, this is probably pay attention to this question. So acceleration 10 newtons can divide by mass 3 kilograms, and you get acceleration. Very straightforward. So later on I will ask you what if there are 20 newtons of force. So stronger force, obviously the loss is stronger force, stronger acceleration. So then of course if 20 newtons of force, still kilogram, 20 divided by 3, and you know what that is. And 20 divided by 3 will be 6.6 meter per second squared. So if you have stronger, double the force, double the acceleration. Now, instead of a 3, if I say, well, it's a bigger mass, instead of a 3 kilogram object, if it's a 6 kilogram, then you will have 10 divided by 6, then you will get 1.3, 1.5, 1.6, okay, 1.66. So this will be 1.6 roughly. You do the math, okay? Meter per second squared. So if you have a bigger mass, so this will be 6. If you have more force, 6.6 compared to original question. So you have a 6 meter per second if you double the force. But if you double the mass, then you get half of the velocity, acceleration. So divide by 6. So this question is very straightforward, and if the force 10 Newton force strength applied to an object of 3 kilograms, what will be the acceleration? That's a straightforward calculation.